compactive effort should be fairly strong. Okay, shortcomings. There's actually no performance-related test. Okay, so basically it's compacted, and basically we make sure that it has 4% air void at the design condition, and that's it. Okay, mixtures which meet the superpave mix criteria can have drastically different performance. You know, we have experience where there are many mixtures that meet the criteria, and some of them do not perform very well. Okay, even though most of them would perform well because there's such a strict requirement on the aggregate, and we compact it to such a high compactive effort. So mixtures which meet the superpave criteria can have poor performance. Okay, the last one that I want to review fairly quickly, I want to look at the time. Are we going over time? Yeah. Okay, we have 6 minutes to finish up the presentation. Appreciate your patience. It's easy to stand up here and talk, but if you're sitting down there, it's easy to fall asleep. Yeah, so I appreciate your patience. So the last one, this is called GTM. Okay, it was developed by Mr. John McRae, who used to work for the Mississippi Highway Department. Okay, it's been used on numerous pavement projects throughout the world. Today, the only country that is using the GTM method is China. There's several provinces in China that are using this method right now, and they have great success. Even though this method was developed in the United States because of the implementation of superpave, this method unfortunately is not used in the United States in design of actual pavements. Okay. It uses a gyratory compaction machine similar to the superpave gyratory compactor. The main difference is that in the superpave gyratory compactor there are 3 contact points. In this method, there's only 2 contact points. Okay, there are only 2 contact points, and so when there's 2 contact points, it has an advantage that if the mixture cannot take this amount of shear stress, this mold actually becomes unstable, and it could wobble a lot. And if it wobbles a lot, it translates into a very high gyratory angle. So when the specimen is compacted, it also plots the angle of gyration, and it becomes unstable. This would wobble a lot, and we'll be able to tell that it's not stable. Okay, and there are 3 types of upper roller. If we use the oil or the air roller, when we compact it, we could also measure the shear strength of the mixture. Okay, and this picture shows that gyratory compactor simulates traffic compaction and also construction compaction very well. As a vehicle moves over the surface, the mixture goes through actually a shear deformation in one direction and then in another direction, and which is simulated by the gyratory compactor very well. Well, there are several things that control compaction. The vertical pressure is called the ram pressure, the gyratory angle, and also the type of the roller could be, different types of roller could be specified, and different compactive effort is achieved by using different number of revolutions, and typically 60 to 200 revolution is specified. Okay, as I said, because there's only 2 roller, if the mixture become unstable, it would be manifested by a high gyratory angle, which is captured by this, the gyrograph, which is plotted. In this test, you plot the gyratory angle experienced by the mole, and it becomes unstable. This angle could increase, and in the test, we take the maximum angle divided by the initial angle, and this becomes the, if I go back, this becomes the gyratory stability index. Okay. If it becomes unstable, this ratio would be greater than 1, and it would indicate instability in the mix. Okay. So if the mixture cannot take such a high compactive effort, the gyratory machine would wobble, and we would measure a high GSI that is greater than 1. Okay, so in this test we measure the GSI. We also measure the specimen height, which could be used to calculate the density, and also the shear strength of the material. It's also measured, the gyratory shear. Okay, I just want to briefly describe the design method in this method. Okay, the mixture would be compacted using this set of test configuration. Okay, it would put in this gyratory compactor set at an angle of 2 degrees, and basically you take this mixture and you compact it, and the compaction simulate the actual construction compaction. Okay, so in the proposed method, you would prepare mixtures at an asphalt content that is around the estimated asphalt content. So one at the estimated asphalt content, and one at 0.5% below, and one at 0.5% above. Okay. So mix the aggregate with the binder at this asphalt content. You put in the GTM machine, you compact it, well, how do you compact it? You compact it until it does not compact anymore. Okay, that's the basic steps involved. You compact it until it does not compact anymore. If the mixture cannot take this compactive effort, the machine would wobble, and you have a high gyrograph. The GSI would be greater than 1, and you know that mixture would be unstable. Okay. Okay. And so you compact it, a mixture that is satisfactory would not be unstable, and the GSI would stay as close to 1. Okay. Yeah. And so the optimum asphalt content is the maximum asphalt content such that the GSI is equal to 1, and the measured shear strength should be greater than the anticipated pavement shear stress, which could be calculated. Okay, if we know the maximum tie pressure, we can calculate the shear stress. Yeah, and a rough estimate is that you take the tie pressure and divide by pi, you get roughly the estimated maximum shear stress. Okay, so this method is a little bit different from the other method. This method, basically, you just compact it until the mixture does not compact anymore, and if it can take such a high compactive effort with no problem, it means that mixture is not going to have problem with rotting. Okay, so the merit of this method is that the GTM compacted mixtures are representative of few mixtures. The gyratory shear value is a measure of the shear strength, and it's related to rotting resistance. GSI value of over 1 indicates instability. So if the mixture becomes unstable when you compact it, you know it right away. Okay. volumetric properties are not needed. Okay. So this is based on a completely different philosophy. Okay. For the other three methods, the philosophy is that at the design asphalt content, the air void needs to be 4%. Okay. The GTM method says that, well, as long as the mixture is stable, it doesn't have to be 4%. It could be 3%. It could be 5%. Okay. So the volumetric methods are not needed. You just need a mixture that would hold up the applied stress. Mixtures are compacted to ultimate condition. Unstable mixtures can be detected during compaction. Okay. The limitation of the GTM mixed design method is that, well, is not used widely, and also cracking performance is not evaluated. So to evaluate cracking resistance, we need to run some other tests. Okay. So thank you for your patience. I'm going to sum up now. Okay. So we look at the four different mixed design methods, look at the properties and their possible relationship to performance. So how can we design an asphalt mixtures that would work? Okay. All right, we mentioned that it needs to be compacted properly. So the first thing we want to make sure is that is it going to be compacted properly? The mixtures should be prepared and compacted to close to the field condition as possible. Okay. And the methods we evaluated, I found that this two compactive effort works the best, either the GTM or the super pave gyratory compactor. The Marshall compactor has some problem. The Veeam has some problem. Veeam, even though give us good compactive effort, it does not simulate traffic compaction or the actual traffic or the actual construction compaction very well. Okay, so we need to compact the mixtures to conditions similar to the field condition, and then we need to evaluate its properties. Evaluate properties need to be good indicators of performance, such as rotting resistance and cracking resistance. So we can use some of the property which seems to relate to performance very well, such as the Veeam S value, Marshall flow, GSI, the shear strength. All these were related to rotting resistance. Okay. And then we can measure things that measures tensile strength, such as Marshall stability, indirect tensile strength. Okay, that could be used to evaluate cracking resistance. But for like top-down cracking, we could possibly use the method recommended by Dr. Roque, which Dr. Bunchai has contributed to this development, the DCSE and fracture energy. Okay, and but whatever we adopt, it needs to be verified with field observation. Okay, so if you suggest some criteria, let's try it out and let's try to see if they match with actual field performance. Okay. Well, and that concludes my presentation. Sorry that I went a little bit over time. Thank you for your patience. And I also invite you to come and visit University of Florida when you come to the United States and Florida. University is about 2 hours drive from Disney World, where it's a big tourist attraction. Okay. Thank you very much.
Thank you very much, Professor. I have one question. As your presentation, you mentioned about the performance in terms of strength or mechanical property.
Right? Yes.
I just would like to ask that other performance like the durability of the asphalt that will maybe deteriorated by UV radiation or something. How can we decide that against that kind of?
Yes, yeah, that's a very good question. So the question is the durability of the asphalt. As we know, asphalt age hardened with time, with service. So you may design an asphalt mixture that would work really well with no cracking, rutting, no problem at all. But a few years from now, we're going to have problem because the asphalt age hardened. Okay, and that's a very good point. I did not cover this aspect in the presentation. Okay, so to evaluate it fully, we would need to take the mixture and age harden it to simulate a condition several years later, and then test the mixture in a similar fashion. Okay, the problem you point out a problem with asphalt mixture is that it age hardened with time. So it's not possible, at least for the present technology, it's not possible to design an asphalt mixture that would last for 50 years. Okay, even if everything is done right, you put it down, then 10 years from now it age hardened, and there's going to be problem. You know, in United States, in the state of Florida, a well-designed pavement would last on the average 12 years. 12 years later, there would be some cracking and so forth, and the material needs to be milled off and replaced with a new layer of material. But how long it's going to last, it's a durability problem, and that's something that needs to be addressed, which I did not cover in this presentation, but that's a very good point.
But for aging that you said is cannot last for 15 years, but that is the portion on the top of the layer.
Yeah, right.
But if we have full depth, like a very thick asphalt pavement, then at the bottom or
would be okay. Yeah, then that's good. There's a design concept called perpetual pavement, asphalt pavement, where the structure is designed to last pretty much forever, but the asphalt at the top will not last forever. So if it's designed properly, all you have to do is every 10 years or 12 years, you remove the top layer and replace only the top layer. Okay, so we don't have to work the whole thing over and over again. Yeah, that's, and so that would be the design to go with asphalt pavement. But with concrete pavement, which I will talk about in my next lecture, we could actually design concrete pavement to last for 50, 60 years with no problem, because concrete does not age harden with time.
Thank you, Professor Thier, to bring the word fundamental. I'm really light because I'm originated in Thai. I think most of Thai engineers completely forget about the fundamental, because everything been doing in US, we follow you, we believe you very much. That's why we forgot the word about the fundamental. In fact, it's very important. I agree with you.
Thank you.
Regarding to your presentation, I come up with something that would be crucial in Thailand situation and even in the Australia as well. Because now we get back to your presentation about the mixed design. In Australia, we still rely on the Marshall mix. Most of every standards in the Australia still rely on the Marshall mix. After the super pair been announced and been used widely in the US, some hesitation happened. What should we go? I think based on your 30-year experience, you should give us some suggestion. I think this would be the situation in Thailand as well. When US change, we curious, should we change? The question is, should we shift from Marshall mix, which everyone in this room know very well in Thailand and still rely on that? Should we shift from Marshall to super pair, or should we stick on Marshall? Because I think most of us still don't know about what kind of the difference in terms of the performance, Marshall mix and the super pair, because I think heaps of money have to be invested if we shift from the Marshall mix to the super pave. And in Australia